Good morning, everyone. Good evening to those of you that are away from the U.S. My name is Michi Oneda. I am with Cypress Semiconductor, and we will be your host today for the third webinar on PSOC analog coprocessor. Today's webinar will cover one of the projects within the PSOC analog coprocessor kit, the Inductive Sensing kit, and also we will cover some topics and slides that we were not able to cover during webinar 2, and these slides will be about the analog system and the analog resources within PSOC analog coprocessor. And today the presenter for today's webinar is Kanan. He is an applications engineer with Cypress who is heavily working with this device. So without further ado, I will hand it over to Kanan.
Hey guys, so I'm Kanan. I work as an applications engineer at Cypress. Work on devices like the analog coprocessor and some of the upcoming devices from the PSOC family. Today is an extension of what we discussed last week. Last week we went through all the analog components of PSOC, and one of the things that we left out last week was the UABs. Which is a universal analog block. So it'll take some time initially to look at the UAB block, what the constituents of the UAB block are, how you could configure the block to act as different components or different functionalities in the analog domain. After that, I'll go into detail on two components that are built using the UAB. Components are use cases of how you could use the UAB, and we have created software wrappers that would let you use them as a VDAC or a filter. So we'll go through those two components, and after that I'm going to go into a detailed discussion on inductive sensing code example. This is a code example that is a part of the analog coprocessor kit. You can also download this from the Cypress website. So I'll go into details of how the analog circuit for inductive sensing works, what the excitation system is, how you sensing it, and all that. So that's gonna give you a insight into how to bring together a whole system inside a PSOC analog coprocessor. Also give you a slight insight into few functionalities of the UAB block, because we do use the UAB block inside the inductive sensing code example. So before we jump into the UAB, just a refresher into what we covered last week. We looked at programmable analog subsystem in the PSOC analog coprocessor. We have a programmable analog block in there, which is the UAB. We have a SAR ADC, which is a 12-bit, one MSPS SAR ADC, a mux that would let you mux all the input lines into the SAR ADC, two continuous time blocks. Each continuous time block incorporates two op-amps, so you could build naked op-amps out of it, or you could use it as a programmable gain amplifier with internal resistors. So that's the CTB. We have something called capsins, which you can use to measure capacitance, which is in turn used for capacitive sensing, touch sensing of touch buttons and sliders and stuff. We also have two low power comparators, which could be used as wake-up sources in sleep. You could use this to wake up your device from sleep mode and an analog signal. That's the advantage of something like this. And apart from this, you have a huge I/O matrix, which lets you take any GPIO on the device into any of these analog functions that you have. So that's a high level on the device. We already covered most of what's in this diagram. What we're going to cover today is the UAB. So the UAB is a switched capacitor block. So the way I look at it is, think of it as so there are two halves to a UAV. Each half has an op-amp, and around the op-amp, I have a bunch of capacitors, which are configured in a switched capacitor mode, which means you have switches around the capacitor that let you, in one phase, charge the capacitor, and in another phase, discharge it. And depending on how you phase the charging and discharging of these capacitors against another capacitor, you could determine the property of this block. For example, if you were to charge the input capacitor, one of the input capacitors, in one phase, and while discharging this capacitor, the next phase, you are charging this capacitor, the feedback capacitor, and then discharging it in the next phase while the input capacitor is charging again. What you're effectively building is controlled charge flow, which is equivalent to two resistors. And hence you would end up building an amplifier using that. So that amplifier would have a gain that would be input capacitor over feedback capacitor. So so that is just one use case of the UAB. You have other use cases where you do not switch the input, the feedback capacitor, and only switch the input capacitor. Then what you're doing is you're controlling the charge flow, but then accumulating it on the feedback capacitor, which is equivalent to a low-pass filtering or an integration kind of nature. So you could use this to build an integrator, and if you were to use two input capacitors and phase them apart, then you would end up subtracting the two signals that come on those input capacitors, and you could integrate the subtracted result. Then you would end up building a delta sigma modulator using that. So there are tons of things that you can build using the UAB. You could just like you build a amplifier, you could have a fixed input impedance, input signal, a fixed reference that comes in as an input. You amplify it, and you keep changing the gain of that amplifier. What you end up building is a VDAC. So that's how you build a 12-bit VDAC using the UAB. There are other blocks that you can, other components that you can build using the UAB, like the second-order filter. Like I said, if you place a capacitor on the feedback and the input switching capacitor, then you build a low-pass filter. You switch that around, you have a high-pass filter. You could build two, using two UABs, you could end up building a band-pass filter. So all these can be built using the UAB. We do have components for both the 12-bit VDAC and the second-order filter at this point. There are more components being built as I speak, which would come in the earlier part of next year, which would be the programmable gain amplifier, a second-order delta sigma modulator, incremental ADC. If you think about the VDAC with the fixed reference input, if you made that fixed reference actually changing signal, you're multiplying that signal with the capacitor values that you set up. So you take the VDAC with the fixed input and you put in a variable input. What you end up making is a MDAC, a multiplying DAC. So you have that also coming up. Summer, a subtractor. So if you put in inputs into each of these legs into the different input capacitors, you could end up building either a summer or a subtractor based on what phase the inputs are being sampled at. Like I said, integrator, and so if you if I have an amplifier and I'm switching in one phase, I will have positive gain. Switching it in one phase for the input, I would have a positive gain. And if I change the switching, so as in change the modulation of the switching frequency, then I would have a negative gain. Meaning, if I were to sample in phase 1 on the input side and discharge in phase 2, I'd be getting a positive gain. And if I were to switch that into charging in phase 2 and discharging in phase 1, then I'll get a negative gain. So that can be accomplished by a single bit in this UAV called the mod bit, which we use in case the mixer, where you could put in a square wave signal, and in the positive or the high of the square wave, you will have a positive gain, and the low of the square wave, you'll get a negative gain. What that really means is you're changing the gain of the amplifier based on another signal, or you're switching between two gains based on the signal, which is equivalent to being a mixer, digital mixer if you think about it. So you could use this to build down mixers. So if you have high frequency signals and you want to cut that frequency down so that you can sample it, or you want to do something with that signal at a lower frequency because the rest of your circuit is working at low frequency, then you could use a down mixer for that. In the application we will look at for the inductive sensing, we will actually have a down mixer use case, and I'll show you once we get there how we are using the mixer. Of course, if you do not have any of the capacitors or the switches configured, you could use the op-amps as naked comparators. There is also another comparator as a part of the UAV, which will give you a comparator output along with the analog output of the UAV. You could build sample and hold circuits, which is equivalent. The whole system is a sampler-based system, so you could build sample and hold circuits with it. So those are the different use cases of the UAV. We will have the VDAC and the second-order filter as components at this point with the creator. The rest of the functionalities are being built as we speak. We should have those components coming out earlier part of next year. So I'm going to quickly brush through two components, the two components I spoke about. The first one being this scanning SAR ADC filter. So we looked at the SAR ADC last week, and how you could set up different channels and how you could have resolutions and ranges and everything set up. But another feature that you can have is to set up a filter at the input stage of each of those input channels for the ADC. In fact, so there's a limitation on when you set this up. You could only set up the filter for the 0th channel of the ADC. And on the 0th channel, you can this filter is set up using the UAVs. So what you effectively do when you set up this filter is you configure one of the UAVs to work as your filter, and also synchronize its input, synchronize its clocks in such a way that the output is switching. And so since the whole UAV is a switching circuit, the output is also going to be switching. It's not going to be a free-flowing analog output. So you need to make sure that the UAV's output is in the same phase as the phase of sampling of the ADC, so that you don't end up sampling in the phase where the UAV's output is a low and not really the signal you want to measure. So when you allocate a UAV as your filter for a channel in your ADC, what you effectively do is you take the UAV and you configure it as a filter, and its output is synchronized now with the channel 0 of the ADC and the sampling of the channel 0. When I say you need to do that, it's not that the user has to do all this configuration of the ADC. The stuff that the user actually has to do is select what kind of filter he needs to configure on the UAV, set up the 3 dB frequencies or the notch frequencies where you want to get the first 0, and you end up having your sampling frequencies also built in because of the ADC and how it's going to sample your signal. Based on that, the UAV's clock is going to be determined. So once you set up these 3 parameters, the display is going to give you what the amplitude response is and the phase response is. So you can change your parameters to fit the type of filter response that you need, and on setting up all these things and building the project automatically. Everything is set up on the UAV, so you don't have to write any amount of configuration code once you use this component. So that's the ADC filter feature. Just a pointer, it's another tab on the ADC's component customizer. So it's in the scan tab that you generally configure all the ADC's parameters. And once you configure the ADC's parameters, you can go into the filter tab and configure your filter, and can enable the filter in channel 0 in the ADC's channel tab, in the ADC scan tab. In channel 0, you can go in and enable the filter there. So that's one use of the UAV. The other use case is that of a VDAC. So, like I said, the UAV can be set up as a gain amplifier, but then you can put in a fixed input, and then you can change your feedback capacitors in such a way that you're gaining the input signal differently based on each of those capacitor values. So that's exactly what the VDAC does. So what we did here is build a software wrapper around that use case and give you a fully tested and characterized component, which is the 13-bit VDAC. So a single UAV would have given you 12 bits of resolution on the VDAC. You could use 2 UAVs and build a differential DAC, which would give you a 13-bit resolution with an 11-bit monotonic output. You could also have, so you can determine what kind of reference you need, what kind of analog ground you are trying to bias your signal against. You can set up the DAC to have a continuous or a strobed mode. In a continuous mode, it keeps strobing every few cycles of the clock. It's going to strobe your output. In an external strobe mode, what you end up doing is you have an external digital signal that you can drive from like a TC PWM or a DMA's end of conversion output, and you could trigger the VDAC based on that. The reason you would use a strobed VDAC is that the data entry into the VDAC is something you want to control, meaning the write into the VDAC might not be happening at right intervals of time because of firmware delays or DMA latency or something. So you don't want your VDAC to refresh at a different point in time, as in you want a more uniform update to your VDAC so that your update frequency is consistent. The reason you want to have update frequencies to be consistent is because most times if you're trying to do waveform generation from the VDAC, your update frequencies something you want to keep as a constant so that you can filter it out, because that shows up as a spike in your spectrum of the output of the VDAC. So generally you would have a filter on the output of the VDAC that filters out the update frequency or the sampling frequency of the VDAC. So in such a case, you would use a strobe signal, which would be your update frequency. And when you use that, you don't have to be worried about when the update actually happens on the register, on the VDAC register. So you could update the VDAC register at your leisure, but then the strobe would make sure that the updates happen at consistent rate, and thus make sure that your filter is correctly designed to the DAC's update frequencies. You also have a output stage configuration, which is a follower or an op-amp. So either you could so the VDAC's output is going to have to go through output follower stage, which uses the CTB that we discussed in the last class. This is op-amp inside the continuous time block. So you would configure it as a follower and use that to provide low impedance output to the VDAC. The VDAC, being a switch capacitor block, has a high impedance output. So you want to give it more. So you give it more of a buffered output, so that something that is driving out of this VDAC can still draw some current out of it. Otherwise, you're gonna bleed into those feedback capacitors and thus cause issues for your output based on loading. So you could have a follower output. Another thing you could have is an op-amp output. What that does is it gives you a path. So the output of the VDAC goes into the op-amp, but then the feedback path is open. Both the feedback input, the negative or the inverting input of the op-amp, and the output pin of the op-amp is provided as external pins, which means you can connect external resistors to it and build a current output for this VDAC. So that's the output stage options that you have. You can also run internal clock, which is the most preferred mode of operation, because the user does not have to set up a lot of stuff. All you need to set up is the frequency at which you want to run your internal clock. That gives you your refresh rate. Or you could have an external clock, which gives you an external pin to the component, which can be driven by another clock signal. You would typically use this kind of external clock kind of configuration when you want to synchronize your VDAC with another digital system. Let's say you have a bunch of signal acquisition systems going on in the background, which are using the ADC and the sequencer, and you want to make sure your VDAC's outputs are getting synced using a DMA at a consistent rate. So you use a combination of your clock source, which is an external signal, and a strobe signal, which would make sure that the VDAC's output is strobed exactly at that point where you need it to be strobed using a digital signal. So those are the different options of the VDAC. The reason we provide the component is we want to make sure all these options are available for all the users, and also tested and characterized to be working in all the conditions that we provide in the different combinations of these options. So going ahead, those were the two components. Like I said, more components are coming up in the next releases of PSA Creator. You're working on most of those components at this point. One of the reasons it takes time for us to put out components is because before we put them out, we generally go through a phase of characterizing them and going through each of the combination of parameters that the component takes, and make sure they give you the expected outputs in all combinations of those parameters. Going to the first one code example of how you're using the UAVs. I want to look at the inductive sensing application that is part of the PSA analog coprocessor kit. This is the inductive sensing is a interesting code example to pick up today, because this involves some amount of I would say slightly more on the advanced side of analog, and also ends up using the UAV, both the UAV halves in the project. So what are we doing here? So the objective of inductive sensing is to sense the presence of a metallic object. A metallic object meaning an object that has ferromagnetic capabilities. So things that are made of iron are generally ferromagnetic. So if you remember from some of our electrical courses, the core of a transformer is generally built out of ferromagnetic material, and the reason for that is its ability to affect magnetic fields. So we're going to use the same property to determine or sense the presence or absence of a metallic or a ferromagnetic material close to a coil. So if you build a coil, the coil will have inductance. associated with it. And the inductance of the coil is determined both by the number of turns and the number of turns of the coil and the nature of the geometry of the coil itself, and the material of the core, which is the permeability of the core. So if you have an air core, which is the case on the left, you will have an inductance, a self-inductance for this coil. And once you have a metallic core, which is a presence of a metal object right next to the coil, which acts or provides itself as a core to the magnetic fields, you end up having a different inductance. Typically, the inductance in this case, in the case when you place a metallic disc, is going to increase because of the presence of this material. So, so that's what we're going to try and do. We're going to have a coil. We're going to sense the metallic object by measuring the inductance of this coil. To measure the inductance of the coil, what we're going to do is we're going to take the coil and make it part of a tag circuit, an RLC resonant circuit, and then we're going to use a signal to excite this circuit and see how the output of that circuit is going to be. What we're basically doing is taking a fixed frequency and measuring the frequency response to the circuit using that. And as the metal object comes near the coil, the inductance changes and the frequency spectrum or the frequency response of the circuit also changes according to the presence of the metallic disc, and hence the amplitude output of the circuit also changes for the fixed input excitation. So for excitation of the circuit, what we're going to do is we're going to use a PWM. So now a PWM puts out a square signal, not a sine wave. But we don't worry about that because the nature of the circuit itself is going to filter out the harmonic content of the PWM's square wave. And once you build the circuit, you would see that the output signal is already a pseudo sine wave kind of output because you've taken out most of the harmonic content present in the PWM's output. So we're going to have a PWM built using a fractional divider, which is a mode of the input clock dividers where you could configure them to be a fractional division. So in this case, it's a divider of 3 and 1 by 32, which means 1 out of 32 phases of the clock output, I'm going to have 1/3 of the divider, and the rest of the 31 phases, I'm going to have 4/3 of the. I'm sorry, the other way. So 1 out of the 32 phases of the clock, I'm going to have 1/4 of the divider, and 31 of the other phases, rest of the phases, I'm going to have 1/3 of the division. So effectively, over the entire phase of 32 clocks, I'm going to get a 3 and 1 by 32 division to the clock. So the reason I do this is I want an average frequency of 7.9175. And the reason I need this is because later I'm going to mix this signal with a 8 megahertz signal, effectively giving me an 83 kilohertz signal. So I want the variation from the 8 megahertz signal to be as minimal as possible so that my down-mixed output is a really low frequency that I can measure using my ADC in an averaged mode and still get the most amount of resolution out of it. So that's the objective. That's why you want to do a fractional divider, so that you can have a small, that is a fractional variation from your down mixing signal. So hence you have this PWM output, which is equivalent. In equivalence going to be a sine wave of that frequency when it comes into the tank circuit. The tank circuit is the tank circuit is designed to have a resonant frequency of 11.15 megahertz. So the tank circuit's peak occurs at 11.15 megahertz, but our excitation frequency is about 7.9175 megahertz. And the reason I'm doing that is because I want to make sure that the frequency that I'm using to excite the circuit is somewhere on the slope and not at the peak. The reason is you want to have a linear movement of a linear response to the output when I move the resonant frequency around that. If I'm at the peak, the movement, the slightest variations would not cause a huge amount of variation on the amplitude. So keeping it on one of the slopes is more useful so that you can get more linear response to your circuit. So 7.9175 excitation frequency. You also have the tank circuit, which is designed for close to an 11 megahertz resonant frequency. You also have a high-pass filter on the output of the tank circuit, which takes the output signal, which is biased at VSS or the ground, and pushes it up to a reference voltage, which is what I want to use as my analog ground for the rest of the sensing circuit in the sensing side, which I'm going to discuss next. So my tank circuit, which is designed at 11.15 megahertz, is going to take that 7.9175 kilohertz excitation voltage, and based on its frequency response, there's going to be an output amplitude associated with it. Now, that amplitude is determined by both the L, which is the 3 microhenry inductance, and also the capacitor, 68 picofarad capacitor. So that's what is determining my resonant frequency, which is 11.15 megahertz. If I were to change my inductance from 3 microhenry to another value, it's going to move my resonant frequency away, meaning it's going to move it higher than 11.15 megahertz. The more it moves away from 11.15 towards 12 or 13, I'm going to start seeing that the slope is moving forward, and hence my 7.9175 megahertz excitation voltage is going to see a lower point on my slope, effectively giving me a lower amplitude. So as I bring in a metal object close to this inductor, it's going to send my resonant frequency to a higher frequency, and hence reduce the output amplitude coming out of this tank circuit. So now, how do I measure the amplitude of this output frequency that is coming out? How do I measure and make sure that's first of all, I want to make sure that is the right frequency I'm measuring, and also measure the amplitude of that frequency. So first to discriminate the frequency, what we do is we use a down mixer with an 8 megahertz input, or the local oscillator clock is 8 megahertz. So your sensor signal coming in is 7.9175 megahertz, and your local oscillator clock is 8 megahertz. Now your down mixer is going to multiply these two signals together, and it's going to give you a subtraction of those two frequencies. While you multiply in amplitude domain, you subtract the frequency domain. So it's 8 megahertz minus the 7.9175. So that gives you 83 megahertz output. That's the down mixed output. One other good feature of the down mixer is presence of a comparator output. This is the comparator output from the UAV. So that gives you, so while the F out gives you an analog signal, the comp out gives you a digital signal, which is high during, which is high whenever the signal is above Vref, and low whenever the signal is below Vref. So it's just a comparator output. The reason we want this output is the next stage, when we use it as a rectifier, the rectifier is nothing but the comparator's output is going to determine the gain of the UAB. So the rectifier is configured in such a way that the gain of the UAB is determined by a modulation signal, which is coming from the comparator's output. So now you have the sine wave output coming out of the F out going into the rectifier. You also have the comparator's output going out into the zero crossing input of the rectifier. So what you're effectively building is something like a synchronous rectifier. So you have a digital signal that determines what kind of gain you want. So every time this guy is high, the rectifier's output is going to gain by 1. And every time it's low, its output's going to gain by -1. So every time this signal is above 0, you're going to gain by 1. Every time it's below 0, you're going to gain by -1, which means you're going to flip the signal. So that's going to give you a full wave rectified output of the down mixer's output. So the down mixer's output is going to now have only one side, which is the rectified output, which you can easily put into the ADC. Plus, having the fact that it is only an 83 megahertz, 83 kilohertz. I'm sorry about that. It's an 83 kilohertz signal. I'm gonna have an ability to scan this at a much lower scan rate. So my ADC can now scan this signal and also average it and get me an amplitude number for the signal. So that's what's happening here. So I have a whole picture of the project here. The PWM's output's a square wave. If you were to measure the output of the tank circuit, you're going to see a sine wave of the frequency 7.9175 megahertz. The high-pass filter puts the same signal at a biased level at the VREF, so that my down mixer can see the whole signal, because the down mixer is going to look at only from 0 to whatever EDD is. So I'm going to be able to see the whole signal using the biasing. And then after I've mixed it using the 8 megahertz, I get an 83 kilohertz signal, which is a much slower frequency than the input to the mixer. And the output of the rectifier is similar to a full wave rectifier. I get a full wave rectified output, which is measured by the ADC. So that's the whole inductive sensing solution. So when you place a metal object right next to the inductor or the coil, the inductance changes, it reduces the amplitude, and you will see that the ADC's output also reduces according to the presence of the metal. The proximity of the metal also changes the amplitude. So you could measure the exact amplitude and resolve the proximity of the metal object to the coil, which could be useful in applications where you want to measure displacement of a metal object over some kind of a sensor. You could also use this for limit switching, where you want to use you want to have a way of sensing the presence of a metal as a form of a limit switch for closed doors, locks, etc. So a lot of applications for inductive sensing, where you want to replace mechanical sensing mechanisms in industrial applications. So that's all I had. Time for questions, I guess.
So that's the end of the